Okay, so let's get on the final for 214. There's 21 questions. Should take about 2 days to finish. All right, so let's look at this guy. Present value of a project is $12,000. Project's life is 15 years at a discount rate of 8.2. What is the project's annuity or annual payment? So we have gone to a lot of trouble to get these guys up and running. So if you remember, all I did here in these cells was to do some verification. So these are the functions. I'm sure they're correct. I think down here I was using net present value to just check something. I'm just going to throw that over to the side for now. So for this guy, I'm just going to take it again, copy it, paste it, and I'll call it final. Problem 1. Oh yeah, yep. Shrinky dink it. Is that better? Okay. So problem, final 1 problem. So we're looking at 3 numbers, 12,000, 15, and 8.2. So let's come back here. 12,000 is the principal. 15, and this is 8.2. So now it's just a matter of which one is the present value. Yeah. So that's that should be the answer right there. So we know it's the annuity. We know it's some fraction. You know, it's approximately 1/15 of 12. It's a little more because the interest rate on there, but that's let's go with that. Okay, so 1419, closest value, there it is. If you could do that in your head, then more power to you. I mean, you almost can. You almost can. You know, if you just started off and did something like this, you could say 12,000 divided by 15 equals, well, 800. You might guess 1,000, but you know that the yeah, you're making 8.2 per year, so that's what it comes out to. Okay. All right. Turbine generator, average head of 275 feet at a flow rate of 19.5, operates 250 days per year, 12 hours per day. The turbine efficiency is 82%, and the efficiency is 94%. The energy is worth $30 per megawatt hour. What's the annual value in thousands of dollars? What week is that? Do you remember?
6, 7. See, that's where I was going when I kept guessing what week was that,
Yeah.
Finally, I just renamed everything.
Let's do it. I'm going to do it right now too. So this is yeah.
You have to do that underscore.
Yeah, you used to have to do that, not anymore. You say it's week 7? This is
that's CAS and LED, that's not week 7.
Week 6, let's try 6. What's in 6? System efficiency, not quite. Hey, pumped hydro. All right, how do we do here? Okay.
I'm just kidding.
All right, so let's just take this whole thing, copy it, new tab, final, 2017, paste it. Let's just dive into the problem. Take this guy, copy that, back here, insert text, found it, text box. I don't think we're going to have to deal with all that power factor stuff. Okay. Head of 275 feet. Okay, so we start with pressure. Hopefully that's not going to screw anything up. Let's just see what happens. 275. We'll just hard code that. We'll just delete this. Just going to do a little strike through on it. Okay, so we've got head goes in, and we know that's an input. 19,500 GPM. 19,500 GPM. I like a comma. Keep it tidy. That's another input. Operates 250 days per year. 250 days. Hours per year, so 6,000.
250 times 12?
250 times 12. Yep. Equals 250 times 12. Tink. 3,000, so that's another input. Turbine efficiency is 82%. So in this case, we're running uphill, right? Turbine generator. Turbine the generator. Okay, so we got. Let's just call this the turbine. Turbine efficiency.
No, that's all downhill.
Well, I know, but I
That's
just.
not uphill, that's all downhill.
Oh, I know. I'm still going to work with what I got. 0.82. So that went in. The generator efficiency is 94. So let's just turn the motor into the generator. The energy is worth $30 per megawatt hour.
You didn't change that number. Screen or something.
94. Oh,
You
thanks.
just highlighted it.
Thanks. Energy is $30 per megawatt hour. Let's do this. Dollars per megawatt hour. 30.
There's your answer right there, your energy cost dollars per year.
Yeah, but I got to make sure where this thing came from. Okay. So the water horsepower, that's our same formula. So this is calculated. Put that in blue. That's calculated. There's our water horsepower. Now there's no pump. So I'm just going to delete that. Delete. There's no belt. Delete that. There's no belt power. Delete that. Generator, motor power. There's no motor. We're not dealing with the power factor. Don't mess with that. Motor repair and power, we don't care. Reactive power, we don't care. Okay, so this is our total horsepower. Now, what we want to do is say, what's our actual, what's our power in kilowatts? Yeah. Let's jam that in. Insert. So this is going to be HP per watt. I like to do it the long way. 746. Let's put that in gray.
You like to do it the long way?
Yeah, I feel easier. Horsepower per watt. So this is going to be watts of watts available. Super power available in watts equals, there's the horsepower times the watts. All right, so that's also calculated. We'll keep that in blue. Dink, dink. And now we'll insert again. Now let's do power.
$30 a megawatt?
Yeah, let's do power available in megawatts equals that divided by 1E6. Put a couple decimals on it. 1 megawatt. And now we'll convert this guy, and this is going to be power out, and again we'll operate in megawatts. So this is going to equal the power available times that efficiency times generator efficiency. Yeah. 1. Put some sig digs on there.
Sig dig it.
You can dig it. You can dig it. And now there's our hours per year. Here's our energy. Let's highlight that too. That was part of the given. And now energy out per year in megawatt hours equals power out times hours per year. It's not in dollars. How do I undollar it?
That would be times 30 again?
Go up to where it says accounting. and
Oh, yeah.
General. Or number.
Yeah, there we go. Cool. Okay, so we've got 2,366 megawatt hours per year. It can be gray. And here's our
Cost.
yeah, and this is our
Cost per month.
well, what's the profit? In dollars. And that equals megawatt hours times dollars per megawatt hour.
Didn't
70.
you have that already once?
Yes, you did.
Oh, did I?
Yep.
Oh,
Yes, you did.
triple check, triple bottom line.
Nothing wrong with that.
All right, so I'll just put that bad boy in bold. That's the answer. Ding, ding, $70,000. 70. Okay. Hey, look at that. An 800 megawatt rated coal plant operates at 66% annual capacity factor. Mercury emissions are 0.1 pounds per kilowatt hour, how much mercury is? Million pounds per year? Come on. You can't emit 1,000,000 pounds of mercury.
This must be one cool.
That's freaking, oh, I'm sorry. Oh, okay, I'm sorry to get distracted.
800 megawatts.
Let's do it, though.
Wouldn't that be 800 divided by 1,000?
Here's your pencil paper, man, bust it out.
800
Don't be distracted by me.
Times 66 times 30.
Double check. Here, you guys, tell you what, you guys work on it for a little bit. I'll turn the screen off and we'll find the answer.
Wait a minute,
I'll turn it on. I'll turn it on.
back on for us.
Yeah, okay, let me do this. Yeah, write down the critical values. This will be good in class. So power equals 800 megawatts. P equals 800 megawatts. Capacity equals 66%. Capacity equals 66%.
0.01.
Mercury is a 1/100th of a pound per kilowatt hour. And let's just assume it runs 24/7, 365. Oh, no, it runs 66% of 24/7, 365. Yeah. Okay, I'm going to turn the screen off. Ready, set, go.
No.
Orem, crack me out, man. Crack me out the door. You got her?
Well, that's what my answer was.
Cool. Let's be right with you.
53, 52.8.
That's what you got?
That's what I got.
Cool. Let me catch up with you here. Hg per kilowatt hour. LBS 0.1. Megawatts.
That's how you done?
Pardon me.
Time's up.
800.
Time's up.
365.4. Energy. How many megawatt hours per year did you get?
Megawatt hours per year? 800.
Well, but your hours per year is 365 times 24. It makes 800 megawatt hours per hour.
But you only have
No, it's
66% of that.
it's
So
800 megawatt hours. It's already in megawatt, it's already in hours. You don't have to do the conversion.
5,000.
Isn't it, let's see the problem.
Hours per year.
This is not correct.
What? Are you looking at the answer?
I don't know the answer.
What are
Well,
you
listen,
looking
listen.
66% of 8,760 is 5,700.
Megawatt. Is it megawatts or megawatt hours?
Times 5,000.
I converted, I didn't go to megawatt hours, I converted to kilowatt hours, but I just did the whole conversion. So if you want me to stop there, I can do
Okay, well, I'm just looking at the whole thing.
because I just multiplied 1 kilowatt times 1 hour to be 1 kilo equals 1 kilowatt hour. That's my conversion factor. Because I changed
But
the
isn't the
kilowatts.
800
I went to
mil?
kilowatts first because we needed that. And then I changed to kilowatt hours.
You got 50?
53.
I got 46. Are you almost there, Shauna?
Well, the way I did it, I come up with what Gary come up with.
Okay, well, let me show you what I got here, folks.
Okay,
This is weird.
but it is weird.
Yeah. We lost, I think I've got all my cursing out on the tape, too. Okay, so let's go back to the problem statement. Oh, my gosh. Is this even close to correct? 800 megawatts, so this is only about, maybe a third the size of Colstrip. Colstrip is 2.2 gigawatts. Colstrip is 2,200 megawatts. And it's operating 66% annual capacity.
I don't have enough information to do that now that I'm looking at it.
Okay. Well, let's just check it.
How many hours is it operating each day?
It's operating 16 out of 24 hours every day, or it's operating May through December, May 1 through December 31st.
That's just.
It doesn't matter.
That's, for me, that's something that's way out there. Because for you to pull that out, I mean, sure, it could operate at those hours, but what if it doesn't?
There's no what ifs. That's how much it operates. It operates 66% of the time.
I see how you got to your answer, and, yeah.
I mean, sit and philosophize about it, but it operates 66% of the time. So, yeah, so we start with, so that's the power.
So capacity factor is what, 6,640 some hours or something?
Why do you have 8,766? Isn't 8,760?
Well, I took the fact that there's
Oh, okay, I get you.
a little extra, yeah.
Leap year?
Yeah, so that's how many hours, so there's 365 and a quarter days in a year, times 24.
Can we look at capacity factor quick?
How so?
on the worldwide internet.
Inner tubes? Okay,
Energies.
let's do it. It's the total divided by the, got it? Okay, so I'll show you one way to do it, then I'll show you another way. So here's the power, and this is nothing more than E equals P, PT. That's all that is. It's just, that's all day long. Energy is power times time.
Okay, you took your steps a little differently.
Yeah, there are other ways to do it. So that's the energy in megawatt hours. It's the megawatts times the megawatt hours. That's if it was running all the time. Now I converted it to kilowatt hours, multiplied by 1,000. Here's the capacity. And so it didn't make 7 billion kilowatt hours of electricity, it only made 4 billion. This was only running 2/3 of the time. 2/3 of the time. Now, this is the mercury output, pounds per kilowatt hour, 0.1. So we just multiplied the kilowatt hours output times the 1/100th of a pound.
Okay. And then how did you get to the 46?
You get the 46, I just divided her by a mil.
Good.
Yeah,
I see it.
yeah.
I
I mean, you could also do it this way,
So go back to time again, it's 365 times what again?
24.
365 times,
That's hours per year.
Did you got me days and hours?
Yeah, hours.
I took the time and reduced it down to the 66% and then multiplied that by the kilowatt hours.
Yeah.
And then the
Right.
0.1 divided by 1,000.
Yeah, you could also do it this way. You could do equals that times that times
Capacity.
that times
1
that.
divided by,
And there's, you've got divided by 1,000, because I guess that was in mega, yeah.
that's kind of what I did.
Yeah.
what's the answer say?
We'll see.
46 million.
I'm going for 46. Okay, 350 megawatt gas turbine operating at full load with a heat rate of 7,500. Natural gas is $4 per million BTU. It's the hourly fuel cost. Let's see how we do. Insert text to box. Okay, so here's your power. I'll do that in megawatts. 350. Full load. Remind me heat rate. Is it kilowatt hours per MMBTU? I think it's, I just can't remember the definition. Let's look it up.
That's BTU divided by kilowatts.
Yeah.
BTU per kilowatts, thanks. BTU per kilowatt. So it's, this is energy divided by energy. So BTUs per kilowatt hours, okay. BTU per kilowatt hour. Okay. and we're given 75,000, 7,500, 7,500. Cost, full load, what is the hourly? So this is going to be, insert, this is going to be energy, this is going to be megawatt hours per hour equals 350 times 1, right? In an hour, it makes a megawatt hour. Yeah, megawatt hours per hour. So the heat rate, so this is, now let's do the energy, this is the energy in kilowatt hours per hour. Yeah, times 1,000. Okay, now the heat rate, so this is BTUs per kilowatt hour. So this is the energy BTUs per hour equals kilowatt hours per hour times BTUs per kilowatt hour, comma, dink, dink, energy cost, let's do this, energy MMBTU per hour equals divided by 1E6, energy cost, dollar per MMBTU equals $4. $4. $4 energy cost dollars per hour equals dink times dink. Dinkity dink dink. $10,000 an hour. Run your plant. You better be selling some electricity. $10,000. Okay. What is the result of the Excel function PMT?
That's the payment function.
Yeah. I think, is it annuity?
I think so.
Yeah.
I guess you could pull it up and just look on the,
Yeah, let's check it
you'll
out.
be able to see it on your little, tell me about,
I don't have payment in here.
you don't have that final one.
I wasn't even using that one.
PMT is present to annuity or future to annuity, so that's annuity.
Yeah, so I think, so you got the rate, the number of periods.
Present,
Mm-hmm. It's got future values sitting out there though, doesn't it? What is calculated as a result of using the, I think it only, I think it only does the annuity. I don't think it'll do the future value.
Well, in here, what I have here, it shows that it does future to annuity and present to annuity is your payment function.
Future to annuity and present to annuity? Okay, so
I would.
what's the result? It gives you the annuity. That's all it gives you.
That's it.
Okay? I mean, all of these are involved, but it only gives you the annuity. Okay?
No, that sucks when you guys do that. Because I overthink that.
I know, I started overthinking it too, but we talked it out, we figured it out. do this one? You remember?
Remember?
It's got losses,
Nine or 11?
it's got losses as a function of diameter and length, doesn't it?
11, 12.
That one might be 9.
Okay, let's check it out.
The Pontevedra.
What was 8 again? Was this pump, this was pumped. I don't think in this guy, we didn't have any losses, did we? So let's just save that, close it. Come on, stop it, just stop it.
You got a function going on.
Yeah, pumped hydro function going on.
It's the payment of the pump. Hey, what's going on? What's going on? What's going on?
Take this worksheet and turn it into one function for me. That would be nice.
Let's just close that guy. I'm not going to use it again. Let's go back in here. Okay, here's week 9. I don't think there's anything in here. This is our heat rate. This is week 9.
See, that's the big problem I was having when I was trying to look through all my stuff. I had them like week 1, week 2, week 3, week 4, week 5, week 7, week 8. And it just didn't help.
CAS.
So I went through them all and renamed them all.
Good idea. Let's see what's in week 10.
Also summarized them all for week 12.
Nice.
PS, K, XLS. Yeah, it's the second part of the affinity law,
Right, okay.
I believe.
Close that one.
It's right. It was right there.
Infinity, okay. What was week 11? Solution, that was EVs. I remember doing that, that was good.
Oh, yeah, it's comparison, 2 CVs to the Guzla.
Right.
Come on, respond.
Excel does that sometimes.
You're not that important. Week 11 was EVs.
That's pretty much it.
What was 12?
12 is,
Your story.
it's your story.
Okay.
It's a summary or whatever. You're on a job interview and you tell them, yada, yada.
What was 13?
You go back to.
CAS 2?
Mm-hmm.
I don't know, I don't have a...
No, 13 was photographic story.
From week 7, right? Or week 4, there's one of the weeks.
Of your,
How do I get a new thing going here?
what do you mean anything?
Well, I need a new tab going so I can look at the final and the problem at the same time.
You gotta split screen it. Click all your tabs and throw it to one side of your computer. All your tabs, not just one.
Maybe let's try logging in again.
Or you can, it's usually the idea.
See if it'll let me. We got to find that because that's important.
But
The pressure losses from flow rates and diameters?
Oh, that's affinity, it's 10. It's the second part of 10.
It is?
Yeah, you had it right
Okay.
there. That
Okay.
says right there, and you said, oh, and you just wrote it down and went on.
Okay.
Maybe.
I'm pretty for sure. So, you see the affinity law tables?
Yeah.
Okay, that's not it. Okay, here we go.
There's no,
Oh, there's no.
Losses there.
Okay, there it is right there.
Yeah, your N1 divided by N2 squared does your affinity loss.
right,
Okay, but.
but I need flow rates and diameters.
Go to 11, go to week 11, because it's next week then.
Good thing you're around, Gary. We would have been here for hours.
It's in EVs?
Yeah, go to the second part of that. There's a P2. There's a P2 there. No,
No.
that's P1. There was one in there that said it was a 5-meter diameter.
I know, yeah.
And you see, that was a problem I had when I named them all, just 1, 2.
Yeah,
3, 4.
when you numbered them, yeah, I know. It's a problem we're having right now.
Made me feel even stupider than I am.
Economic basics, economics applied, supply and demand, power factor, systems efficiencies and losses.
Are you going to be in this one?
No, because you're not going in the water.
Too early. Demand side management, capacity factor, pump storage, maybe?
Maybe.
7?
Pull it up, let's look at it. I was almost for sure it took one of the SMUD.
That's compressed air.
I remember that.
Vertically integrated.
That's the LED problem.
Yeah, LED.
That was a doozy. That was a doozer.
All of them.
It was like a, when the middle was off.
Compressed air and LED, okay, that was 7. Compressed air, okay, so week 8.
Pump hydro.
That's what I initially thought.
Come on,
Pump
baby.
hydro, pump hydro.
That's fine.
8.
8. Mhm. Weird. It's almost there, isn't it?
Not there, it's not it.
We did do one that had the pipe diameter.
Right.
Yeah, it was, but it used the problem from the previous week too, because it was an addition to it.
Yeah. Prius, okay. So it's not 8.
Is it 9?
We're being very systematic here.
Elimination.
Compressed air, it'd have to be the second part of it.
Yeah. Pressure band, we did that. Discussion. Huh? Okay, it's not 9. Come on. Me too. Can't be variable frequency drives and not electric vehicles. The heck, is there a way to search inside of this thing?
Nope.
No, good luck.
It's not there. You gotta get the baby? All right, well, I'll keep turning on this. Where was it? Where is it?
Is it
I thought it
like
was.
in the beginning, like maybe 4 or 5, or?
What
No.
was the first pumped hydro? It was 140 gallons per minute, or 140,000 gallons per minute.
It was week 8.
That was week 8.
Let's look again.
Yeah. Weird.
I wish I brought
Was
my
it in the
computer.
quiz?
Ooh.
Off of our homework? Because you know the quiz debriefings? I think that might have been one of
Friction head.
There it is.
Hallelujah. Hallelujah. Praise the Lord.
This is not a timed final, correct?
No?
Okay.
No.
It's going to take me a while to find all these assignments.
Yeah.
Friction head,
So are we going to have a lecture next week, or is it just,
I'll be here.
next week's the last week of class, isn't it?
Yeah.
not me? This is a tough semester, material-wise.
It's my last one.
Mine too.
Mine 3.
Really?
I don't know. I think they're going to fire me so hard. I mean, they're trying so hard.
That's
And
not what I heard. I talked right with the head of the material science program, and he was for sure that you're gonna get integrated over there.
Material science? That's not,
He
It's
was
not?
positive they're gonna scoop
could be,
you.
but
well, I mean, it used to be. What?
He's positive they're gonna scoop you over there for something, which I don't know.
I'd be surprised. I mean, they're laying off 100 people. We'll see. I'd love to stick around. I really, really would.
Honestly, there's no engineering here. I mean,
It's,
everything.
that's
that
sweet,
they-
Shauna. I'll see you.
Everything that they do over there is chemical.
It has a big chemical bias.
Pharmaceuticals and chemicals.
Yeah.
They're not interested in any energy, in any flow of any measure. They don't care.
I know. I know.
I need to get in the rooms. I need to return this. I
Okay.
wanted to hook this up and show it to you so that you can actually see it for yourself. This is a neat thing. It like has magnetivity here, magnetism. There's nothing here, nothing out here. You'd think it'd be even out here, but it's not.
Let me finish this problem so Miss Shauna can feel better. Fifty percent there. Final.
Okay, what was that?
Okay, so here's diameter, feet, 10. Speed, F PS, feet per second. 9. Provides hydraulic energy to a turbine running at 10 megawatts. Assume that the generator is 94. Turbine, 0.88. So the generator is going to deliver 10 megawatts. So 10 megawatts has to go out.
Yeah, that's, gosh. The equation you're looking for is the beginning of A, because you're gonna have to look for the heat. You're gonna have to.
That 3960 water horsepower deal?
Yeah, you're gonna have to move that around, not the water horsepower, but you're gonna have to move around. Because you've got your feet per second times your elevation for your head. What is it?
I gotta draw this thing. Here's the pipe. Here's the turbine. Here's the generator. And here's 10 megawatts coming out. So the power, this is power out.
12 feet per second.
Okay. Head equals, what did we say?
That's what you're looking for.
Oh, thanks.
That's
G equals 10 feet, perfect, okay. So the power in, so efficiency equals P out over P in. So P in equals P out over efficiency. This is P out. Power in megawatts. So P in equals P out eta T eta G. P in equals P out divided by? Divided by?
Yeah. Because you took 5 together and you
Equals 10. I always have to triple check on this dang thing. Okay, so 12 megawatts has to go in. Equals 12.08 megawatts going in. So the water, we need to have the water horsepower. So let's get the water horsepower. So let's go from megawatts to water horsepower.
No, you're not gonna be able to get it that far.
Well, don't these formulas get you to horsepower though?
Or your water horsepower is gonna be feet, so you're gonna buy feet before you find horsepower. Total.
Well, I wanna know.
No, yeah, okay, you find it, I'm sorry.
Yeah, I think if we get our horsepower in, that we'll know yeah. Power in, water horsepower,
So what's 749 watts?
let's do, power in, let's just do it the long way. Kilowatts equals that times 1,000. Insert power in horsepower. Or no, it's just horsepower per kilowatt equals 0.746. And now we can get to this guy. There's fewer horsepower per kilowatt, so it equals that times this. It's going to give us horsepower. There's our water horsepower. Okay. So now we do have to work backwards and figure out if we've got.
Is that,
So this is the losses. So friction head is related to the water velocity squared. Friction head is flow over pipe area squared.
9 feet,
What are the units on friction head? PSI?
so I think it's feet. Because we're looking for feet, elevation is in feet. We got, what's your,
Yeah.
feet per second, so that's pretty much what it's gonna be, it's gonna be in feet. Because you're looking for your elevation. Isn't it? In feet, elevation head in feet. It says it right there on the question.
Right, yeah.
So, you remember that stuff we were looking at for problem, I think it's 8? You divide it all by 3,660 or something?
Yeah, I do.
That's the equation you'll need. You got everything down with that equation.
Flow over pipe area squared. Can't be this simple.
That's friction head, that's not elevation head.
Equals well, it's the loss. Yeah, you're right. It's friction, so it doesn't really matter if this pipe is vertical or whatever. It's just that the water's flowing at 9 feet per second through a 10-foot diameter pipe. So we got to get the area in square feet. Let's get this in here. Insert radius feet equals that by 2. Insert area feet squared equals dink times pi. That's fine. So let's just look it up here. Friction head.
for 100 feet of pipe. See, what is a required elevation head? They're two different things, I believe.
What's the elevation head to get the,
Well, the total head is the elevation head minus the friction head. Or is it the friction head minus the elevation? One of the other is. I believe, don't quote me on your chocolate. You're like a candy pusher over here. How's the chocolate?
Well-
I was like, no, I don't want any chocolate.
I know,
I'm just
I know.
gonna set it right here. I saved you some. I'll take it. I'm not sparing you chocolate.
all right, so here's where we are, and unfortunately, I don't think we made a whole heck of a lot of progress on this guy. I think there's an error somewhere, but let's just see where we are. So we did the pumped hydro, and what we started with, we got the pipe 10 feet in diameter, 9 feet per second, maybe somebody can spot the error, delivering 10 megawatts of output to the grid. So the system, we've got our generator, we've got our turbine, we're putting 10 megawatts out. That means we need to put 12.08 megawatts in, and it's coming from this pipe that is 10 feet in diameter, moving at 9 feet per second. So in our spreadsheet, here's our kilowatts. So 12 megawatts is 12,000 kilowatts. Here's our horsepower per kilowatt. This is our water horsepower.
Can we look at the area again on that?
Yeah, so let's look at the area. So the diameter says it's 10 feet in diameter. Its radius is 5 feet. So the area is pi r squared. So I got 5 times 5 times pi, 25, about 79 feet. Now the velocity is 9 feet per second. So the flow is 707 cubic feet per second. There are 7.5 gallons per cubic foot. 7.5 gallons per cubic foot. So that gives us 94 gallons per second. Multiplied by 60, that gives us 5670 gallons per minute. So the friction head so gallons per minute is going to be the horsepower. This 3960 just is messing it up. Start trying 3960 divided by gallons per minute.
There was, we looked through all of that. I think it was in the 8 resources.
Yeah.
The resources for chapter 8.
Yeah. Well,
There was a big equation.
pumped hydro, we did the same thing here. We got the water horsepower. That's the head in feet times gallons per minute. Water horsepower, in this case, we're dealing with about 105. This is a much larger system. Well, I was coming up with this giant answer, 11,318. I'm just going to hit that and move on. So, sorry we didn't get any further along. Okay, select all features that can affect energy use in a pump system. So the pipe length, sure. Type of fluid, absolutely. Affect energy use. Well, the longer you use it, the more energy. Pump efficiency. Elevation of fluid, I think they're all there. Okay. Project's net value considers all expenses and revenues throughout the life. True. The utility tree structure has a demand period of 30 minutes. The company's monthly demand was 30 megawatts. How many kilowatt hours were consumed in the demand period? Utility rate, monthly demand was 30 megawatt hours.
3.8 megawatts times
Oh, wait, hang on.
5 hours.
We have to save. It's no good. Have you seen this before?
You're not connected to your internet connection.
Must have just blipped out.
It's just the auto-save feature, but I don't understand.
I've never seen that. And so here's what I came up with. I'm going to take a break here in a second after I wrap this up. So utility rate structure is demand period of 30 minutes. The company's monthly demand was 3.8 megawatts. How many kilowatt hours were consumed? So here's what I did. So here's power, here's time. This little line is basically showing here's our demand, and there are 720 hours in a month, and there are therefore 1,440 demand periods per month. So obviously I can't slice it that thin, but there are 1,440 of these. Here's day 0, here's day 30, and there are 48 demand periods per day, 1,440 demand periods per
So
month.
that's area under the curve between the line.
Yeah, all the area under the curve, this is our energy.
But the demand that you're getting whacked on is, it'd be the area under the curve between your power factor.
Well, so this it's not really, it's kind of weird because it's not a financial problem. They're not saying this is how many dollars you pay every time you go over. It's just saying this is it said that our monthly demand is 3.8 megawatts. So what I did was I just averaged the 3.8 megawatts over the entire, all of the demand periods. So there were 1,440 demand periods. So when we divide 3.8 megawatts by 1,440, that's 0.0026, so 26 thousandths of a megawatt, which is 2.6 kilowatts. So I figured that the average power, this is basically P bar. P bar, average power is 2.6 kilowatts, which sounds about right. You know, that's small business or a large house, 2.6 kilowatts. Now, if we multiply power by time, so there's 720 hours per month, so 2.6 times 720 equals 1872. Boom. Okay, I'm going to take a break. We can keep going if you want.